This is a chapter review and quiz review for Changes of State, chapter 23. A pig has no pores, so what it will do is it'll play in mud, get its skin wet, then the moisture will evaporate, taking the body heat with it. So evaporation is a cooling process, especially relative to the pig. On the other hand, condensation is a heating process. Here we have an old style radiator, and you have steam inside the radiator. And when the heat is given up by the steam, when it condenses inside the radiator, the heat is given up to the room, and the room becomes warmer. So condensation is a heating process as opposed to evaporation, which is a cooling process. A camel's best source of water is in its oversized nose, with an inside structure that recaptures most of the moisture in the water-saturated air coming from its lungs. So it withdraws water from its own exhaled breath. Now, fog and clouds, how are they formed? Warm air rises. As it rises, it expands. As it expands, it cools. As it cools, water vapor molecules begin sticking together after colliding rather than bouncing off one another. If there are larger and slower moving particles or ions present, water vapor condenses upon these particles and we have a cloud. Fog is basically a cloud that forms near the ground. Flying through a cloud is much like driving through fog. Fog occurs in areas where moist air near the ground cools. For example, moist air that has blown in from over an ocean or lake may pass over cooler land. Some of the water vapor condenses out of the air as it cools, and we have fog. A key feature of fog and cloud formation is a slowing down of water vapor molecules in air. So it's condensation, which is, again, is a heating process. Let's go back over this just a little bit. You see where it says warm air rises? Well, warm air rises, and it's cooler in the upper atmosphere, so you would think that the air would not expand but contract. But it actually expands because the pressure is less, so the volume of air will become greater. So it's a very dynamic process, but understand this, that when the warm air rises, it expands. And the water molecules will have less and less kinetic energy, so they're going to coalesce and form water droplets that will eventually fall as rain. So that's very, very important. So the first paragraph here is vital. Here are various types of clouds, the stratus, the stratocumulus, cumulus, cirrus, various types of clouds that form as a result of the amount of water vapor that is going into the sky and how far above the ground the clouds form. Notice the very large thunderhead. And here is a slide which shows some of the dynamics involved in rain clouds. Here you can see how enormous the cumulonimbus clouds are compared to the cumulus. That's a jet flying at about 30,000 feet or 10,000 meters. And you can see that the top of the thunderhead is well above where the jets might be flying. So a cumulonimbus, oftentimes a thunderhead, can be enormous. Here is a picture of someone getting out of the shower. It says, if you feel chilly outside the shower stall, step back inside and be warmed by the condensation of the excess water vapor there. Remember, condensation is a warming process because the droplets are going from a gas to a liquid, and it's giving off that excess heat in order to form the water vapor, the droplets. This is actually a very, very important and dynamic picture. It says the motion of molecules in the bubble of steam, much enlarged, creates a gas pressure that counteracts the water pressure against the bubble. Now, let's look at this a little bit more closely. For the bubble to form, the vapor pressure inside that bubble has to be greater than or at least equal to the hydrostatic pressure outside the bubble. The hydrostatic pressure is the atmospheric pressure plus the pressure from the liquid. Now, if it's water, where water has a naturally very low vapor pressure, that's why it has a very high boiling point, 100 degrees is high, where alcohol is only 79 degrees for a boiling point. Alcohol has a much higher vapor pressure, so it will boil at a lower temperature. Now, if I bring down the atmospheric pressure down very low, water can boil at room temperature because the atmospheric pressure is lower and the bubble can form. So think of it as a fight between the vapor pressure inside the bubble and the atmospheric pressure outside the bubble. So if you're in the Himalayas, up high where you have lower atmospheric pressure, it will boil at a lower temperature, etc. Now, water forms ice crystals that are very hexagonal in nature. If you ever look closely at a snowflake, you would see, and you use the magnifying glass, you would see a beautiful crystal that is basically hexagonal, six-sided, and the picture demonstrates that very, very clearly. Although streams can freeze over in cold weather, most often they don't. Why? Because streams are usually fed with warmer groundwater. They're also moving. The moving of the stream helps to prevent the freezing. But the groundwater, it'll come up from the ground and it'll be a little bit warmer of water. And that will help matters tremendously in terms of preventing freezing. Okay, now this is a very important model. Figure 23.9. The apparatus shown can be used to demonstrate that water will freeze and boil at the same time in a vacuum. A gram or two of water is placed in a dish that is insulated from the base by a polystyrene cup. Continued boiling results in a lowering of temperature until the freezing point of approximately 0 degrees Celsius is reached. Continued cooling by boiling causes ice to form over the surface of the boiling water. Lowering the pressure can cause boiling and freezing to take place at the same time. This must be witnessed to be appreciated. Frozen bubbles of boiling water are a remarkable sight. If some drops of coffee are sprayed into a vacuum chamber, they too will boil until they freeze. Even after they are frozen, the water molecules will continue to evaporate until little crystals of coffee solids are left. This is how freeze-dried coffee is made. The low temperature of this process tends to keep the chemical structure of coffee solids from changing. When hot water is added, much of the original flavor of the coffee is preserved. Figure 2310, regulation allows the wire to cut through the ice, but leaves the ice in a single solid piece. So that's called regulation. It will simply refreeze on itself. It's not a problem. Speed skater glides on ice. Ice skating works because metal skate blades glide with very little friction over a thin layer of water on the ice surface. At one time, scientists thought skaters created the water layer by melting the surface layers of the ice through the pressure of their body weight. However, recent studies disprove that explanation, and it is now believed ice is always slippery because the molecules in its topmost layer behave like liquid water. Either way, old theory or new, the skater is skating on liquid water. Physics in the kitchen. The egg test. Physics can help with even the simplest of all cooked creations, the boiled egg. Test the egg for freshness by placing it in water. If it sinks and lies on its side, it's fresh. If it floats, it's rotten. The egg loses density as it ages because it loses moisture through pores in its shell, eventually becoming less dense than water. To test that the egg is raw, spin it on a tabletop. If it wobbles, it's uncooked. The wobbling indicates that the yolk is moving within the egg, thus changing the egg's center of gravity. Eggs sometimes crack while boiling due to an air pocket inside. With heat, the air pressure in the pocket increases enough to crack the shell. If you carefully pierce the egg's big end with a small, clean pin before boiling, it won't crack. Finally, be sure you actually boil the water. You can heat an egg indefinitely at low temperatures, but it doesn't cook. Cooking requires exceeding a threshold temperature so that the long-stranded molecules of the egg becomes cross-linked. That's why an egg won't cook by boiling at very high altitudes. The boiling water is not hot enough to cook the egg. Here is the phase changes involved in the three phases of matter. We're not including plasma here. Energy is absorbed when change of phase is in this direction to the right, going from solid liquid to gas. It's absorbing energy. Energy is released when change of phase is in this direction. That's from right to left, going from a gas liquid to a solid. Remember, change in the internal energy of a substance causes the change of phase. Now remember what internal energy is. We'll do that on the next slide. I'll remind you. Heat of fusion is either the energy needed to separate molecules from the solid phase or the energy released when bonds form in a liquid, physical bonds, and change it to the solid phase. That's heat of fusion. So remember, you understand what heat of fusion is and also heat of vaporization. And remember when I say the change in the internal energy of the substance causes the change in phase. That's very, very important, right out of the book. I put this in here to remind you about internal energy. 21.4. In addition to the translational kinetic energy of jostling molecules in a substance, there is energy in other forms. There is rotational kinetic energy of molecules and kinetic energy due to internal movements of atoms within molecules. There is also potential energy due to the forces between molecules. The grand total of all these energies inside a substance is called internal energy. A substance does not contain heat. It has internal energy. When a substance takes in or gives off heat, its internal energy changes. Absorb heat may make the molecules of a substance jostle faster. In other cases, as when ice is melting, a substance absorbs heat without an increase in temperature. The substance changes phase, the subject of chapter 23. Remember, when a substance absorbs energy, but its average kinetic energy does not increase, in other words, its temperature, which is the average kinetic energy, that means that the potential energy of the substance is changing. So a change of phase is actually an increase or decrease depending upon the direction of potential energy. So here I have figure 23.12. The graph shows the energy involved in the heating and the change of phase of 1 gram of water. So you can see how it's gaining heat. Look at going from melting. It's gaining 80 calories, as opposed to water, it's gaining 100 calories, going from 0 to 100. And then look at the vaporization, 540 calories per gram to go from water at 100 degrees to steam at 100 degrees. Absolutely outstanding. Figure 2313. When a car is washed on a cold day, hot water will freeze more readily than warm water because of the energy that the rapidly evaporating water takes with it. The 540 calories, 2,255 joules, required to vaporize a gram of water is relatively large amount of energy, much more than is required to change a gram of ice at absolute zero to boiling water at 100 degrees Celsius. Although the molecules in steam and boiling water at 100 degrees Celsius have the same average kinetic energy, steam has much more potential energy, 540 calories worth, because the molecules are free of each other and are not bound together in the liquid. Steam contains a vast amount of energy that can be released during condensation. The large value of 540 calories per gram explains why under some conditions hot water will freeze faster than warm water. This occurs for water hotter than 80 degrees Celsius. It is evident when the surface area that cools by rapid evaporation is large compared with the amount of water involved. Examples are a car washed with hot water on a cold winter's day, and a skating rink flooded with hot water to melt and smooth out the rough spot and refreeze quickly. The rate of cooling by rapid evaporation is very high because each gram of water that evaporates draws at least 540 calories from the water left behind. This is an enormous quantity of energy compared with the 1 calorie per Celsius degree that is drawn for each gram of water that cools by thermal conduction. Evaporation truly is a cooling process. Refrigeration is also a very big part of all of this, as is applications of phase changes. A refrigerator's cooling cycle is a good example of the energy interchanges that occur with the changes of phase of the refrigeration fluid, not water. The liquid is pumped into the cooling unit, where it is forced through a tiny opening to evaporate and draw heat from the things stored in the food compartment. The gas is then directed outside the cooling unit to coils located in the back. As the gas condenses in the coils, appropriately called condensation coils, heat is given off to the surrounding air. The liquid returns to the cooling unit and the cycle continues. A motor pumps the fluid through the system, where it enters the cycle process of vaporization and condensation. The next time you're near a refrigerator, place your hand near the condensation coils in the back or the bottom of the refrigerator, and you will feel the heat that has been extracted from the inside. An air conditioner employs the same principles. It simply pumps heat from one part of the unit to the other. When the roles of vaporization and condensation are reversed, the air conditioner becomes a heater. A device that moves heat is called a heat pump. There's a picture of a refrigerator, figure 23.14. The refrigeration cycle in a common refrigerator keeps the inside cool. So study that for 30 seconds and we'll go to the next slide. Firefighting. Firefighters regularly enter burning buildings to save lives and property. In order to perform their job effectively and safely, firefighters must be knowledgeable about the physics of heat. The most common fire control is dousing a flame with water. In some cases, a fine mist is more effective in quenching the fire. Why? Because the fine mist readily turns to steam and in so doing quickly absorbs energy and cools the burning material. Properly dealing with flames saves lives, including their own. To firefighters, the physics of heat is much more than classroom assignment. It's a matter of staying alive. Job opportunities exist for firefighters with city or county fire departments and the National Forestry Service.